Previously, we talked about how we're able to oxidize alcohols in order to form different carbonyl compounds. We saw how we can take a primary alcohol and oxidize it to produce an aldehyde, which if we then undergo another oxidation reaction, we are able to generate a carboxylic acid. Again, similarly, if we had a secondary alcohol, we are able to oxidize this once to generate a ketone. Also, we mentioned how we are able to now reduce these carbonyl compounds back to the original primary or secondary alcohols. And how do we do this? Well, we can either utilize a strong reducing agent like lithium aluminum hydride or a slightly weaker reducing agent like sodium borohydride. In the case of going directly from a carboxylic acid to a primary alcohol, whoa, what is that arrow? In the case, let's give this a second. In the case of going directly from the carboxylic acid to the primary alcohol, we would have to, in the case of going directly from a primary carboxylic in the case of going from a carboxylic acid directly to the primary alcohol, we would have to use lithium aluminum hydride, that very strong reducing agent, and the second step would be reacting with water. Now, if we wanted to, on the other hand, go from our aldehyde to our primary alcohol, we could once again either use the lithium aluminum hydride that we just talked about, or as an alternative, we could actually react with NaBH₄, sodium borohydride again, in water. That is an alternative. And in the case of our reduction of a ketone back to a secondary alcohol, we have again those same two options. We could either, for the first step, react with lithium aluminum hydride or sodium borohydride, and then that second step remains the same, where we react with water. So now, let's take a look at the actual mechanisms for these reduction reactions. So when we first draw out the structures of these, metal hydrides here, which are strong nucleophiles, which is why we're able to use them as these reducing agents, what we'll see is when we draw out the structure, right, let's start off with the lithium aluminum hydride. So we'll draw the structure for this. We'll have our aluminum bonded to the 4 hydrogens, and we can have this sort of lithium here floating in solution, and we have to remember to draw the negative charge for our aluminum. And now if we draw the structure for our sodium borohydride, you can see that it looks very similar. We have our bromine at the center, bonded to 4 hydrogens, remembering to draw out that negative charge for our bromine, and in this case we would have our sodium ion floating here in solution. And so we can see the structure here are very similar, and thus the mechanisms are also going to be very similar, if not the same, except which reagent here we're drawing out. And so here for the video, I will go through the mechanism for our lithium aluminum hydride. And if you would like, back at home, you can try to draw it out for sodium borohydride as well. So let's say we had our secondary alcohol, which we oxidized it to form a ketone. And now, for whatever reason, we would like to reduce that ketone back to our original secondary alcohol. How would we do so? Well, we'd have to take our secondary alcohol, right? We'd have to take our ketone. And reduce it. So the first step, remember we talked about, would be reacting with lithium aluminum hydride, which then would produce a structure that looks something like this, which we then react with water in order, once again, we should make sure to include that ion here. And once again, this would then result in the generation or regeneration, right, of our secondary alcohol. Like this. So now let's look at some of that arrow pushing that would be a part of this mechanism. Again, this shouldn't be very long. So what we'll see is if we draw our ketone, R1, R2, we have this carbonyl, and now we draw out that aluminum hydride. Keeping charges and ions in mind. We'll see a set of 3 arrows kind of jumping around here. So again, let's make these lone pair pretty explicit. So what we'll see is the lone pair on this oxygen is going to go on to attack our aluminum. And while this happens, we can see that the hydrogen here is going to go on to attack this carbon, which then pushes the electrons that make up this double bond back onto this oxygen. So this set of 3 arrows, we can kind of see almost like a circle, is going to result in a certain product. So let's see what that would look like, because it is kind of complicated with all these arrows going on. We don't see any arrows really going to R1 and R2, so let's keep that the same. R1, right, and R2. Now let's go from in order what the first thing we started with. We started off firstly with an arrow going from the lone pair here to our aluminum. So that means we know that there's an oxygen here that now has a bond to an aluminum. And this aluminum also has some hydrogens on it. But how many hydrogens are there? Well, you can remember that once this bond forms, we also see a bond forming between this hydrogen and our carbon, which means our aluminum here is only left with 3 more hydrogens. So we'll have LiAlH₄, again, minus, keeping in mind that lithium still around here. And we can see that we have the hydrogen here forming a bond with our carbon. So we should remember hydrogen here. And finally, we can see that this original double bond is now a single bond because we have the electrons that make up this double bond jump on as a lone pair to our oxygen. So we now only have a single bond. And so this is what we're dealing with. So now this is the sort of intermediate where we have R1, R2, H, and we have our oxygen bound to our LiAlH₄ minus. So now it is this intermediate that we react with water. So upon reaction with water, we end up producing our alcohol. So you have R1, R2. So now this basically expunges or kicks out this LiAlH₄, this aluminum stuff we got going on. Instead, we end up with a hydroxyl here, and this hydrogen just stays in place. So in this way, we're able to regenerate, or if maybe not regenerate, we're able to generate our secondary alcohol from our ketone here. So now feel free to try to draw out the similar arrow pushing scheme using sodium borohydride. Really, there is no difference there. All you really have to do is just put a bromine here. But again, just for your own, practice, right? You can draw this out with lithium borohydride, with lithium aluminum hydride, with sodium borohydride. Just practice drawing out mechanisms and drawing out the structures, with maybe even substituting the R1 and R2 with actual R groups, just so you get into the practice of actually drawing out different structures and, keeping track of everything. But anyway, that brings us to the end of this video. If it was helpful, please show your support by liking and subscribing. Leave in the comments any questions you may have, as well as suggestions for future videos, and I will see you in the next one.